Hello and welcome to the heat transfer course Convection. My name is Wilco Roves, and in this video we will look at the forced convection in internal flows and in specific the heat transfer coefficient in laminar fully developed flows. The learning goals in this video are as follows. First of all, I want you to have the ability to calculate the heat transfer coefficient in laminar flows under fully developed conditions and in a simple way for the case of a constant heat flux boundary condition. The second part is the ability to distinguish between different flow configurations and choose the proper correlation for the heat transfer coefficient. I would like to go back to the image we have already seen, the flow going here from the left to the right, the wall side heat flux, and we are looking at the case of constant heat flux, and we know that the fluid temperature rises, and with a constant heat flux we also know that the fluid temperature, so the mean temperature of the fluid, will increase constantly and linear. The wall temperature will show a little bit different behavior. We will start here at the inlet with the wall temperature to be exactly the same as the fluid temperature, because the boundary starts at the thickness of 0, and then the temperature increases first rapidly and finally reaches a constant difference between the fluid temperature and this. We already have learned this is a pinch that depends on the thermal conductivity, heat capacity, channel size and velocity profile. So now we are interested in calculating this heat transfer coefficient. What do we need to do to calculate the heat transfer coefficient? Of course, we need to know the heat flux, but this is a boundary condition that is described. So in the next step, we need to know the temperature of the wall and the temperature of the fluid, and we know that this is the caloric mean temperature of the fluid. So let's do that. We know if we want to draw it, it looks like this. We have seen it in the previous lectures, but I would like to go here exactly into this topic. We are interested in the fully developed region, and let's check if we can calculate analytically this coefficient C2. So what are the steps and the procedure? We have to look at this equation and we have to look at the missing parts, the wall temperature and the fluid temperature. How can we calculate these? So first of all, to calculate these two temperatures, we need to determine the radial temperature profile in the pipe flow. And in the next step, we have to calculate the caloric mean fluid temperature, which is sort of the integral of the radial temperature profile. So let's start with the radial temperature profile. We assume first, or that's what is already described, the heat flux is constant, so the caloric mean temperature increases linearly in axial direction. The temperature at any other location will also increase linear with the same slope at any radial location. Thus, the temperature gradient, not the temperature itself, but the temperature gradient in radial direction needs to be a constant. And we know that the change of the axial temperature dt dx is directly coupled to the heat flux and the flow of heat capacity m dot Cp and the size of the channel. And this, of course, with the mass flux here, depending on the property of the on the area and the velocity, where u is the mean velocity of the flow. So what kind of equation do we need to describe the radial temperature profile here? First of all, we are looking at the steady state condition. We omit the diffusion in axial direction, so we only have the advection in x direction, and we assume that there's only conduction in radial direction taking place because the velocity profile is uniform and there is no velocity in radial direction. So the equation that we have to solve for is the following. We have on the left side here now the convective flux, and on the right side the diffusive flux in the two different directions of the coordinate system. If we want to solve this equation, we have to include the knowledge that the temperature in x direction is increasing linearly depending on the heat flux that we provide, and we can directly plug this into the equation. And we also know the velocity profile of a laminar pipe flow. This is from the fluid dynamics lecture, so the velocity is equal to 2 times the mean velocity times 1 minus r squared divided by r squared. R squared here is large, that's the radius, and the other one is the coordinate. And the coordinate system, of course, starts at r equal to 0 in the center of the pipe. So the first mathematical step is to check what can cancel out. Here we see we have rows on both sides. We have CP on the upper and the lower part. We have U here on the top and on the bottom. And in this sense, we can already reduce the complexity of the equation a little bit. And we can bring now the radius here to the other side. So we have radius here and radius by the power of 3. And now we see that we have on the left side the radii, and on the right side we have the temperature derivative. So we can do a separation of variables, integrate the two sides with respect to the radius, and solve for the temperature. So the first step, the first integration, will lead to the integral of the r, which will be 1/2 of r squared, from r by the power of 3 will lead to r by the power of 4, and then we have the integration constant of C1. If we want to solve for the integration constant of C1, we have to look for a good boundary condition. So at the end we will have two boundary conditions, the one in the center of the pipe and the other one on the surface of the pipe. But the simplest one is, of course, the boundary condition that there is symmetry. So the derivative of the temperature with respect to r at the location r equal to 0 is equal to 0. And because we directly have an equation where we have the temperature derivative, we can plug that in. So here is 0, and to be 0 on this part here, C1 also needs to be 0. So we can solve for that. We have the equation for the temperature derivative as shown here. And if we simplify this equation a little bit, we can put the coefficients just inside the equation. So we have 2 divided by r by the power of 1 minus r by the power of 3 divided by the large R by the power of 3. So in the next step we have to integrate this again to get the temperature profile T of R. Again we introduce a new integration constant C2. If we want to solve for C2, we use the other boundary condition as mentioned before for the wall temperature. So we have here the T at the location R equal to large R, so at the pipe wall we have T wall. If we include this in the equation, we can solve for C2. I don't want to explain everything in detail. You can look at the slides later on. You see that there is an explicit equation for C2 depending on the wall temperature. And if we put that in our equation, we have finally here an equation for the temperature profile in radial direction. This temperature profile in radial direction, as you can see, depends on the wall temperature T wall. So we need to know the wall temperature, and we also need to know the caloric mean temperature, what we have discussed before, because we are interested in the two temperatures, the wall temperature and the caloric mean temperature, to calculate the heat transfer coefficient. So that's the second part that we're doing right now. You see here from the last videos we have talked about the definition of the caloric mean temperature. It's a mass flow averaged temperature, or heat capacity flow average temperature. You see rho Cp on the top and the bottom. We cross this out immediately because the fluid properties are constant throughout the pipe flow, and we integrate this with respect to the area of the pipe. If you want to do that, now there comes a little bit of mathematical calculations. Don't let me go into that too much. You see we plugged in here the velocity profile, we also plugged in the temperature profile, and if we do that we have to rearrange a little bit, and you can see here immediately that the factor before the temperature of the wall, it's identical on the top and the bottom, that crosses out completely. And here the other factor we have to integrate from 0 to r on the top as well as on the bottom. And if we look at only this part here, we see that there will be just a numerical factor coming out because the only variables we have is a radial coordinate, which we integrate for, and the radius of the pipe. If we do that with the boundary conditions that at r equal to 0 and at r equal to r, so that's a pipe area that we are integrating for, we finally get the median temperature, the correct average temperature of the fluid is equal to the wall temperature minus 11th by 24 times the heat flux q dot double dash times the radius divided by the thermal conductivity. So with this knowledge, we can do the next steps to calculate the average heat transfer coefficient. To do that, we need to find the difference, so we have to include this in the equation for the heat flux, and you see this is directly the equation of the heat flux. It couples already the heat flux to the temperature difference between the wall and the mean temperature of the fluid. So if we just rearrange this, we have the equation q dot double dash is a factor times T wall minus Tm. And in this sense, we know that this factor will be the heat transfer coefficient, so we can replace it by alpha, and alpha is now 24 divided by 11 times lambda divided by r, so it's 4.36 lambda divided by the radius. And if we look at the dimensionless heat transfer coefficient, then we have to include this in our equation here. Nusselt is alpha times the radius divided by lambda, and then we come up to a factor of 4.36. And you see, for the fully developed velocity profile, the temperature gives a constant Nusselt number. Now, we have looked at the case, and we have seen that we can calculate the heat transfer coefficient now for a case that we have a constant heat flux, and there is a mathematical solution if we have an explicit solution for the velocity profile. This diagram here shows a similar case, but not for the flow in a pipe, but the flow between two parallel plates. So you see here that both happens. We have here the inlet region where the heat transfer coefficient drops linearly in the logarithmic scale. So in fact, it will decrease exponentially and approach the constant value. There are a few important dimensionless numbers here. Of course, we already had the Nusselt number as the dimensionless heat transfer coefficient, the Reynolds number, which describes the velocity, or which describes the ratio between the inertia and viscous forces. But here, of course, also it describes how the flow of heat capacity is traveling through the pipe. We have the Prandtl number, which describes the ratio between the boundaries, so the thermal boundary layer and the viscous boundary layer, and the multiplication of the Reynolds number and the Prandtl number will be the Peclet number. To show this diagram, of course, there are a few assumptions. So first of all, the fluid properties are constant, and there's no shear thinning or no temperature dependencies of the fluid properties. The same image can be now drawn for different cases. The cases before showed the case of the constant heat flux, but we can also look at a constant isothermal temperature. So if we prescribe the temperature on the surface, then we see that the final value will be a little bit different, 3.66 for pipe flow, but also the complexity to calculate this value is a bit higher because we cannot a priori tell that the gradient of the temperature in axial direction is coupled to the heat flux and the flow of heat capacity. And in this sense, we can calculate, or we can use the following correlation to calculate the Nusselt number for the conditions of a pipe flow in an isothermal surface. And we see here another coefficient, which is also important to know what it stands for, and this coefficient accounts for a lower or changed viscosity at the wall compared to the viscosity of the liquid. Just imagine you have a liquid like oil that loses or that has a strongly reduced viscosity at the wall. Then you will change the velocity profile because the shear near the wall or the velocity increase close to the wall is much higher. So you will come to a more plug flow-like velocity profile. And in this sense here you have an intensification of the heat transfer coefficient because the viscosity at the wall is lower than the viscosity of the bulk liquid. If we have constant heat flux, there's a general rule that we can assume that it's about 20% higher compared to the constant temperature value, and the final value we have just shown that one here for the case of the mathematical calculation, so it's 4.36, and we can also use this factor if you want to account for a change of the viscosity due to the liquid. Now we can have a very common case in which the heating is directly starting at the beginning of the section or of the pipe, and in this case both the heat or the hydrodynamic boundary layer as well as the thermal boundary layer will develop at the same time, and due to that, because they are developing at the same time, of course the correlation will be also a little bit different, describing the heat transfer in the inlet region. The heat transfer finally here, and for the case that both the hydrodynamic and the thermal inlet boundary have fully developed, it's the same as we have seen before, the 3.66, but here in the inlet we have a little bit of different behavior, and this behavior is accounted for in the following correlation. Just make sure that you're using the right correlation for the right boundary conditions. What happens if we have a more complex case? Just imagine that we have here again a pipe flow or flow between two plates, and we have obstacles in between. These obstacles, if this is a flow in between two plates, can be just cylinders that are placed in the center and that of course affect the velocity profile. We have seen if there are no cylinders present, the heat transfer coefficient drops here linearly in the logarithmic scale and then approaches a constant value. If we look at the case that we have those cylinders placed in between, we see a similar behavior. So first of all, there is a drop in a linear region, and then finally it approaches a constant value. This constant value, as you can see here it's below 10, is higher because we press the liquid by the cylinders that are placed in the middle closer to the wall, and so there will be the velocity profile near the wall will be faster, and as such there will be a higher heat transfer coefficient. And we also see that there is a variation in the heat transfer coefficient. Always these top parts here are below one of those cylinders because there the fluid flow near the wall is very high, and then it drops in the region where the fluid flow re-established to become a pipe flow. So you see there is a chance that the heat transfer coefficient is not severely affected, at least the behavior, but if we increase the fluid velocity and it comes to the formation of vortices, this plot here is now an instantaneous plot of the velocity. So there is a vortex shedding off on the left side here and here on the right side. And if we go further in time, then there is a vortex shedding off here on the lower side and here on the upper side. So this part will be an unsteady flow behavior, and you see as soon as we are in an unsteady transient flow behavior, the correlations or the behavior of the Nusselt number is completely different. We see that it is not following a constant slope for different Prandtl numbers. We have different behaviors. So this is just important to keep in mind that behavior changes drastically as soon as we have mixing due to an unsteady flow behavior. So this can not only be caused by an unsteady flow behavior, but also by a three-dimensional flow behavior. This will also change a little bit, and you can see here in this video the change between an unsteady and steady flow behavior. Here you see some of the ink is going to the left side, some of the ink is going to the right side, or to is traveling through it. So this is now an unsteady flow behavior of a flow configuration where we have obstacles in the channel that change the or influence the flow between the two parallel plates. And you can see that there's a critical Reynolds number above which the fluid flow becomes unsteady, so it changes from a steady behavior towards an unsteady behavior, and this change will also drastically affect the transport of heat or also mass in the channel. What we have not talked about is the case of a turbulent pipe flow. This is shown here. Now for an isothermal wall, you can see that there is also a correlation given. It's also given in the book of equations. Major differences in the turbulent and laminar regime is the exponent of the Reynolds number. Just check it for the laminar flow. You will see a completely different behavior compared to the turbulent regime. Just make sure if you're using these equations that the conditions are met, so that all the dimensionless numbers are in the right range. You can see this equation here is valid for a specific range of Prandtl numbers, for a specific Reynolds number, so it should be above the critical 2300. And of course, because we are looking at either inlet or non-inlet sections, this shows that you should be beyond the inlet section, so the length should be larger than the diameter. And if you have correlation, you can see this looks more complicated. You can use a more simpler equation compared to the one above, and that's this one here. It shows a similar behavior, but you can see the validity of this equation is a bit different. It starts at a higher Reynolds number, and it also needs to account for longer inlet lengths. So after a longer inlet length of L being larger than 10 times D, you can use this equation here. With that, I'm at the end of the presentation. I have a few questions of understanding. So first one would be, why is the heat transfer coefficient constant in a fully developed region of an internal flow? And the reason for that is basically that the heat transfer coefficient describes the transfer between the wall temperature and the medium temperature of the liquid. And for a case, for instance, if you look at the constant heat flux, both temperatures rise in the similar way, and as such, the heat transfer coefficient becomes constant. What are the major steps to calculate the heat transfer coefficient in a fully developed region? So the first step is to calculate the temperature profile. And from the temperature profile, if we integrate that and calculate the correct mean temperature, we can directly assess the heat transfer coefficient. Last question, what can result in a loss of self-similarity of the heat transfer behavior? So the first point that can lead to a loss of self-similarity is the start of unsteady flow behavior, as we have seen that with the obstacles placed in the fluid channel. Another possibility is 3D mixing. So if we have a three-dimensional flow configuration with complex inlay structures, then this can also lead to a loss of self-similarity. Finally, I would like to propose an extra task for you. You have seen in one of the slides that the Nusselt number for parallel plates is 8.235. If you like, you can try to calculate this by yourself, prove this by calculating the velocity profile and the mean caloric temperature, and then rearranging this to the Nusselt number. And maybe if this is not too complex for you, then you can think about other geometries and flow configurations for which you can determine a laminar velocity profile analytically and then calculate the Nusselt number. And with that, I would like to thank you for your attention and have a nice day.